Welcome back to CS 111. In this lecture, we're going to look at a pretty fundamental computer science concept, recursion. We'll see what recursion is, we'll explore an example or two here, and then we're going to see how recursion compares with another approach to repeatedly running code, loops. When we need to solve problems that involve repeated steps, there's two major ways we can go and implement a solution. The more traditional way is to go and implement what's known as an iterative solution. This is one that goes and uses a loop to go and repeatedly execute a chunk of code. As an example here, I have a method that goes and takes a parameter n, and then it goes and prints out the numbers from n down to 1 per line. So the iterative solution of this problem here is to go and have a while loop, and while n is greater than 0, we're going to print out n, and then we're going to go and decrement n, and then we go and repeat that. Eventually we'll get to the point where n is 0, and then we're going to fall out of the loop, and then our method will return and be done. There's another way that we can go and look at this sort of situation though, where we need to go and repeatedly execute sections of code, and that's called recursion. Recursion is another way that we can go and solve these problems. With recursion, we go and break a problem into two or more pieces. Inside a call to our method, we're going to attempt to tackle one of the pieces ourselves. So that might be, with this example here, we want to be able to count down. The piece that we're going to tackle here is saying what the number is. But then we go and place a call to the exact same method to go and solve the other piece or pieces that we were not able to solve. So we're going through here saying the number, this is the part we're doing ourselves, and then we're going and placing a call to that same method, having it solve the rest of the problem. So if we're trying to count down from 10 to 1, I'm going to go and say 10, and then I'm going to go and place that recursive call saying I want to count down from 9. In that call, it's going to say 9, and then it's going to go and place a call to count down from n minus 1, or 8, and so on until we get to what's known as our base case, where we go and say the part here that we're doing ourselves, we're saying 1, but then we don't go and recurse anymore. At this point, this method call is going to return, and then we're going to have just a series of returns working our way back to the original method call. These calls are what the recursive name comes from. When we go and place a call to the same method, that's a recursive call. And when you're going and using recursion to solve problems, you can end up many layers deep with recursive calls. So if we want to try to go and express this cartoon in code form, we can have a method that we're going to call countdown, and it's going to take a parameter n. When you go and implement problems recursively, you're basically always going to have at least one parameter, if not multiple parameters, because that's how you're going to go and share what part of the problem each call needs to go and solve. So the part of the problem that we're going through and solving here is this first part, where we're going and printing the number. So we're calling println, and we're printing n. The recursive part here is where, as long as n is greater than 1, we're going to go and call countdown, so the same method, and pass it the value n minus 1. So initially we'll go and call countdown with the value of 10. It prints out the number 10, and then it goes and calls countdown with the value of 9. It's going to print out 9, call countdown with 8, and then we get down to our base case, and that's where our recursive calls stop. So that's where we're here on our cartoon, and then we start having those returns working their way back up the chain. So let's see how things actually work when we go and execute our countdown method. And we'll assume that we're going to start off with passing an argument of 5. So n is going to be equal to 5. What's going to happen here is that at the top of the method, it's going to go and print out the number 5 because that's our first actual line of code inside the method after the comment there. Then we're going to go and evaluate to see if n is greater than 1. And if it is, we're going to go and place a recursive call to subdivide the problem, which in our case basically means just go and print more stuff. Since 5 is greater than 1, we're going to have a recursive call to count down with a argument of n minus 1. So n is 5, 5 minus 1, we're going to go and call countdown, pass it the value 4. We're going to keep on repeating that process, going through and calling n minus 1 each time. So at each call, it goes and prints out its own bit, and then it goes and places a recursive call to go and print out the remaining numbers as we go and count down. So countdown of 4, we'll call countdown of 3, we'll call countdown with 2. Countdown with 2, we'll go and call countdown with 1. And when we get to this case here, since 1 is not greater than 1, we're going to stop going and placing recursive calls. This is what's known as our base case, the one where we stop actually having those recursive calls. And in our case here, what would happen then is this method is going to go and return from countdown with 1. Since it's not going and placing a recursive call, it's just going to come down here, hit the end of the method, and it's going to go and return. In our countdown example, the countdown method is a void method. So it's not going to actually go and return any particular value when we go and complete each call to countdown. It's just going to return back up the chain that it is done. So what is going to happen though is that we have a stack of calls. So we have this stack here where 5 called 4 and 4 called 3 and 3 called 2 and 2 called 1. These ones that came earlier in our chain here, which are actually going to be the lower levels of our stack, those calls to those methods cannot be completed until any of the methods that they called have also completed. So countdown of 2 can't finish until it gets the result back, in our case just basically saying that it was done because it was a void method when it went and called countdown of 1. What will happen is when we've actually reached that base case, things are going to go and start working their way back the chain with the results. So here we're just going through and having void value come back because this was a void method. And eventually we'll get to the point where all of the calls to the smaller values of n in the chain return their value, and then the original call to countdown with n equals 5 can also go and return. While you can use recursion with void methods, like we did with our countdown method, more commonly you'll see it used to go and break apart a larger problem where we need to go and do some sort of mathematical operation here. So let's go and take a look at a case where rather than returning void from our method calls, we're actually going to return a value. We're still going to do a pretty simplistic example right now. We're going to go and create this function that we're going to call recadd or recursive add. And it's going to tell us how many of the number 1 we need to go and add together to get n. Now obviously we know that in order to get n we have to add together n ones, but we'll have a recursive method that'll figure that out for us. So the way this method is going to work here is when we go and call recadd and pass it the value n, that's going to lead to a recursive call with recadd of n minus 1. That's where we're going and breaking it into a smaller piece. We're going to take the result from that and we're going to go and add 1. Our base case is going to be where n is equal to 1. At that point we know how many 1s we need to add to get 1, which is going to be 1. So we don't have to recurse anymore. We can just go and return our value. So let's see how this works. We're going to start off with initial call to recadd and pass it the value 5. That's going to go and break things into 2 pieces. the part that we already know the answer for, the 1, and then the part that we're going to have to go and recursively figure out. That's the recadd with n minus 1. So since n was 5, here we're going to go through and call recadd of 4. And then we're going to keep on breaking things apart into a 1 plus recadd of n minus 1. So we get 3, and then recadd for 2. We get down to 1 plus recadd of 1. And that's going to be our base case. So with this base case, we're going to go and return the value that we already know the answer for. So that's going to be 1. And then that's going to go and basically work its way back up the chain. So recadd of 2 is going to be equal to 1 plus the result from recadd of 1, or 1. So we know how to solve that now. We get recadd of 2 is 2. And then recadd of 3 is going to be 1 plus the result 2 that we got. That's going to return 3. Recadd of 4 is 1 plus the result 3 we got. We get 4. Recadd of 5 is 1 plus the result 4 we got. And that's going to be 5. Now, when we're going through and executing here with a recursive method, we actually do need to get to a base case at some point. It can be potentially a number of recursive calls before we go and get there. But there does have to be some point where we no longer go and place any more recursive calls and we can start returning. If we get to a case where we go and restart returning, we're in good shape. If not, we have kind of the recursive implementation of an infinite loop. What'll happen is if we never get to the base case, our code is going to go through and continue trying to place recursive calls until the computer is actually going to run out of room in the stack to keep track of all those calls. That leads to a situation called stack overflow. There's a finite number of calls you can keep track of basically when your program is running, and eventually if you have something that is going and recursing infinitely, it will go and run out of space, and that'll bring your program to a halt. So as you saw on the previous diagram, when we go and place a call to a recursive method, and that method has to go and place a recursive call to solve part of the problem, execution on that original call is paused until it gets the result back from the child call. So if we go and call recadd and pass it the number 5, our call for recadd to 5 is going to do a little bit of work, but as soon as it goes and calls recadd with 4, recadd of 5 is going to have to sit there and wait until recadd of 4 returns with the result. That's going to go through and pause execution on that call, and that's going to go and build up that call stack. So this is where, if things don't lead to a base case, we're going to have infinite recursion. You can see the call stack if you go and use your debugger. So you can see here, for example, I've got a main method where I'm going and calling recadd. And in this case here, I'm going and calling it on line 6 of the file. Recadd on line 23, which is actually going to correspond with this line in the source code file here, goes and places a call to recadd for the n-1, and then that one goes and places a call to recadd. And so until we get down to this base case, and that's at line 26, because I had set a breakpoint during execution on this return current line. So you can see here this stack just goes and starts building up. And with the recursive problem, having just 5 or 6 recursive calls, that's a pretty small number. A lot of times you'll see recursive methods where you may end up with dozens or hundreds or even more calls. Calculating the result of factorials is one of the classic use cases for recursion. So just as a reminder, a recursion is where we have a non-negative integer n followed by an exclamation point, sometimes pronounced bang. And that's something that we can go and expand to say n times n-1 times n-2, kind of just keep going through and decrementing n until we get down to where we have 1 as the last thing that we're going and multiplying. By definition, 1 factorial is equal to 1, and 0 factorial is equal to 1 as well. So if we have a number like 4 factorial, that would be 4 times 3 times 2 times 1. This is something that we can pretty easily go and compute using a loop. We need to have our method go and take a parameter that's going to specify the value of n we're trying to calculate the factorial for. I've got this result variable that just keeps the running result of our product, and then we're just looping backwards. So if we're saying like n equals 4, we'd have an initial pass here with multiplying 4 times result, so that's going to give us 4. Then 3 times 4, that'd be give us 12. 2 times 12 is 24. And then 1 times 24 is 24. So the result of 4 factorial is 24. So we know that n factorial is equal to n times n minus 1 factorial. So for example, if we have 5 factorial, that's equal to 5 times 4 factorial, as I've got shown on the slides here. This part here is really a clear setup for having a recursive method. The part that we're solving ourselves is the n, and the part that we're doing the recursive call for is to go through and compute the n minus 1 factorial. We said earlier that we know that 0 factorial is equal to 1 and 1 factorial is also equal to 1. Those are the base cases for our recursive algorithm. Those are the values that we already know the answer to. So if we have a method that we're going to call fac, just as an abbreviation for factorial, and it goes and takes a parameter we'll call num. If we go and call that with num equal to 1 or num equal to 0, we're going to go ahead and just return 1. If it's any other value that's allowed for num, and by definition with the factorial it should be a positive or at least not negative, we want to go and place a recursive call to fac with num minus 1, and we're going to go and multiply that by num, as we saw on the previous slides where we went and broke things apart. So each time we go and place a call to fac, we're going and solving part of the problem. And we can go and have however many calls we need to go and subdivide this problem until we get down to the base case, and then we're going to go and combine the results, multiplying the return value from the call to the child times num as we come back up our call stack. So let's see how things work when we go and try to use the fac method to solve a factorial, starting with 5 factorial. Here I'm going to place a call to the fac method with a value of 5 for my argument to find 5 factorial. That method is going to go and subdivide the problem to 5 times 4 factorial. So for that 4 factorial, we're going to call the fac method again and pass in an argument of 4. And we're going to go and continue to subdivide that problem until we get down to where fac of 2 is going through and equal to 2 times fac of 1. Fac of 1 is a base case. It's a value for which we know what the answer is, and we don't have to go and place any more recursive calls to go and solve things. So at this point in time, we'll be able to start going and returning values and working our way back up our tree. Fac of 1 is going to be 1, so we can go through, plug in the result 1 for that method call fac of 1, and then that's going to allow us to solve fac of 2. So fac of 2 is 2 times 1 factorial, which was 1, so we get 2. And then we can go and just work our way back up. So we get 3 times 2 is 6 for fac of 3. For fac of 4, we get 4 times 6 is 24. For fac of 5, we get 5 times 24 is 120. So just the return values from our smaller pieces of the problem get combined and returned back up our chain until we get back to our very first call to the recursive method. And that's where we get our result of 120 for being 5 factorial. So here I've got side by side a iterative loop-based implementation of solving the factorial and our recursive implementation. Our loop implementation here basically just has one for loop that goes and drives everything. With the recursive implementation, we're checking to see if we have one of the base cases, and if not, then we're going and placing the recursive call. These are both fairly similar in terms of length of code, and the complexity is probably roughly the same between the two. You might argue that the recursive implementation is a little bit simpler since it doesn't have this loop, but there's not a whole ton of difference one way or the other. If we go and look at these, though, sometimes a deciding factor in terms of how you might implement can be how closely does the implementation go and resemble the problem you're trying to model. So if we're trying to go through and model n factorial equals, n times n minus 1 times n minus 2, well, that, and we kind of especially then go through and figure that, that ends up with n times n minus 1 factorial, that looks a lot like our recursive implementation. So this might be a little bit easier one to go and understand. But that's really kind of a subjective measure. Since we've seen that solutions that we can implement via loops can generally also be done via recursion and vice versa, let's dig a little bit more into when one might be better than the other. There are a lot of similarities between both approaches. In both cases, we're going to end up with a gradual approach towards termination of the program. So if you have a loop, you're going to have a counter or something that's keeping track of which iteration you're on, and eventually you're going to keep on marching down to a point where the condition for going and continuing in the loop becomes false. With recursion, you're going to keep placing calls to simpler and simpler versions of the original problem until you get to the base case when you stop recursing. Both loops and recursion can run into problems with infinite execution. With a loop, especially if you have a while loop, it's possible to go and have something that's going to loop infinitely if the loop's condition never becomes false. With recursion, you can go and have something where the recursion keeps on happening if you never converge on a base case. Both of these are normally the result of some sort of programming error. There's something that you're not doing right with your code or with your logic. With an infinite loop, sometimes the program may just continue indefinitely. With infinite recursion, generally you're going to get to a point where you'll have stack overflow because you've got so many calls deep, and that will go and terminate the program. When you're going and trying to solve a problem, there's not always a clear-cut answer as to which solution is better with recursion versus a loop. To a large extent, it's just a matter of personal preference. If there's a certain style that you tend to like better, that's fine. Sometimes, just because of the nature of the problem, it's easier to go and understand what's going on if you were to implement it as a loop, or perhaps to implement it recursively. When you're going and coding, it's good to have a solution that's easy to understand, so that can kind of steer you one direction or the other. Sometimes, though, you can run into performance issues with a particular implementation, and that might lead you to favor one style or another. Depending on the type of problem you're solving, one issue that can manifest itself with recursive implementations is that you end up with sometimes exponential numbers of calls. So let's say that we're trying to go through and implement a solution to determining the Fibonacci series of numbers, where each number is the sum of the two values that are prior to it. Each time we go and have a level of recursion, so essentially we're trying to go and generate the next number in the Fibonacci series, that goes and doubles the number of calls that we have. So if we're trying to generate the nth number in a Fibonacci series, we have 2 to the n number of calls. And as n gets big, this becomes ginormous. If we're trying to go through and calculate the 20th Fibonacci number, we're going to have about 1 million calls. If we get to where we have the 30th number, that's about 1 billion calls. And even if we're on a super fast computer, that's still going to go and grind things to a halt. Even if we don't run into Stack Overflow, just having that number of calls is an immense amount of work. So that's probably a solution that's not going to be a good way for us to go if we end up with exponential time complexity. Sometimes when we're going through and writing our implementations, we can do some caching of work or structure our calls so that we can make use of data from a previous pass. That can be one helpful way to go and reduce the number of calls. So if you don't have to go and sit there and repeatedly go and compute the same value every time, that can help to improve your time complexity. But sometimes with recursion, there's just not a good way around very high growth rates. That's not to say that iterative solutions are perfect either. There's some types of problems that recursive solutions actually work out better for than ones that are based on a loop. One example that we're going to take a loop at here in a moment is if we have a chain of singly linked nodes and we need to go backwards through that chain. So in the opposite direction of where our next node pointer points. Let's go head over to Eclipse and we're going to take a look at an example. Here in Eclipse, I've imported the node iteration project from this lecture's starter code. This project contains our code for implementing a linked version of a queue. I took the code from our lecture there, and I made one minor tweak with going and renaming the linked queue class to printable linked queue to reflect the new methods that we're going to go and add to this class. We want to be able to go and print a queue both in sort of first in, first out order, where the oldest items get printed first, and where the newest items get printed first. So basically last in, first out type mode. What we're going to do here is we're going to code these implementations up both iteratively using loops and recursively so that you can see the difference. We'll go ahead and start off with the iterative loop-based implementations, since those are going to be closer to what you're more familiar with. These are going to look a lot like what we've done with our toArray method, at least this first one here. I'm going to create a public method that will have a void return type, and I'm going to call this print oldest first loop, so it describes what it's doing. And we're going to go and iterate over each of the nodes in our chain here for the queue in order to go and print them out. So we're going to go and iterate through nodes, printing each on a line. So like we've been doing so far, we'll go ahead and create a current node variable, and I'm going to set this equal to my front node. And then I'm going to have a while loop to go and iterate over the chain. We'll loop while current node is not null, and inside of here we're going to go and print the contents of our current node. So I'm going to call system.out.println, and I'm going to tell it that I want to go and print the value from current node.getData. Once I've gone and printed the value from the current node, I want to go and advance to the next node. So I'm going to say current node equals current node.getNextNode. And that's basically it for this method. Go ahead and add some JavaDoc. So we print contents of queue with oldest items first. This approach here is pretty straightforward. We have this one loop to go over each of the n items in our queue. So this method is going to go and run in big O of n time. So it's about as good as we can hope for. Let's go and take a look at a loop that's going to do basically the reverse of this. It's going to go and print the newest items first. So this will be a public void method, and I'm going to call this print newest first loop. This method is going to have to work a little bit differently because our nodes are singly linked. They only allow us to go in one direction. So that works out great when I'm trying to print oldest first, but when I'm going against the flow with newest first, it poses a little bit of a problem. What I'm going to have to do here is actually go and nest a pair of loops. The outer loop is going to go and iterate for each of the nodes that we have. I'm going to make it be a for loop, and I'm going to say int I equals 0, while I is less than size. We'll go ahead and increment I. So this loop is going to run once for each of the nodes that we have in our queue. Inside of this loop, we're going to have another loop, and its job is going to be to iterate to the appropriate position for the items that we're currently looking at. For this one here, I can't just go and blindly loop until current node becomes null like I did with our other method. I'm going to have to keep track of how many times I've gone and iterated, because I want to make sure that I go and stop when I'm at the right place. Every time through, we're going to go and start at the beginning of our chain. So I'll create this var current node. I'm going to set equal to this dot front node, and notice that for each separate node we're going to restart at the beginning here. I'm going to have another for loop nested inside here to keep track of how far down I need to go. So I'm going to say int j equals 0, and we're going to go and have this one loop while j is less than this dot size minus I minus 1. The minus 1 part reflects that we don't need to actually go and iterate over to get to the first node. We're starting on the first node. The minus I part here is so that with each successive loop iteration of the outer loop, we're going to go fewer nodes into our chain, because that's going to correspond with where we have our older nodes coming towards the front as we get further in. When we're starting off and printing the newest ones, we've got to go all the way to the end. But as we get further down our list here, when we're getting the older ones, they're going to be closer to the front, so I need to do fewer iterations. So that's what the minus I does. We'll go and increment j here, and inside what we're going to do is just advance our nodes. So we'll say current node equals current node dot get next node. Outside of this for loop here, where we're going and advancing our node, but still inside the outer loop, we're going to go and print the contents of our current node. So I'm going to say system.out.println, and I'm going to go and call current node.getData. So basically, we're going to have this outer loop that's going to run one iteration for each of the nodes that's stored in our queue's chain. Inside, this inner loop will get us to the right spot, and then once we get to the right spot, we'll go and print the value from there. So this is what we need to do here to go and print the items with the newest things first. Now, there's a big difference in performance between oldest first and newest first because of this inner nested loop. Each of these loops, since they're tied to the number of items that we have in our queue, is going to run in big O of n time. Since we had just a single loop here, our oldest first method ran in big O of n time. But down here, we have a inner loop that runs in big O of n time, and that's inside of an outer loop that runs big O of n times. So big O of n times big O of n gives us big O of n squared time. So we say that this print newest first loop method runs in big O of n squared time. which is much slower than our oldest first implementation. As it turns out, recursive methods work out very well for cases where we're trying to iterate over a chain of linked nodes going backwards. And that has to do with the fact that when we have a recursive call to a method, execution of that particular method call is going to have to wait before it can finish for the result to come back from any recursive calls that it goes and places to the smaller subproblem. In our case, the smaller subproblem is the next node in the chain. So what's going to happen here is we'll place an initial call where we'll start off with our front node. The front node is going to go and place a recursive call to the second node. That'll place a recursive call to the third node. We're going to go through and print out the value of the nodes after the recursive call. So that means that the recursive call to handle the next node in the chain has to have completed before we go and print out our own value. So that basically kind of allows us to work our way backwards through going and printing stuff out. Let's see how this is going to actually work here when we coded it up, and I think this will make it a little bit clearer for you to understand what's going on. I'm going to go and use two methods for my recursive implementation. When we have a recursive method call, we're normally going to have a method that will take at least one parameter, and that's where we're going to specify what little part of our subproblem that method is supposed to handle for that particular call. Sometimes what you'll also see done, and what we're going to be doing here, is we're going to go through and create another method that kind of serves to kick off the recursive calls. This just makes it easier for somebody else to go and use our recursive method. Right now I'm going to focus on doing the recursive method first, and then we'll go and code up the method that goes and kicks off everything. So the recursive method itself I'm going to make be protected, because I don't want somebody else externally to go and call this directly. I want them to go and call my kickoff method. So I've got this protected. It's going to be a void return type, and I'm going to call this print newest first recursing. So we're going to do the case here where we need to work backwards through our chain. And it's going to go and take a singly linked node of type T that we'll call current node. So this is going to allow us to go and subdivide the problem into smaller pieces as we work our way down the chain. I want to make sure inside of here that we actually have a live node. So if the node is null, that's actually going to be basically our base case when we'll go and stop placing recursive calls. So I'm going to say here, if current node is equal to null, then I'm just going to go and return. And since this is a void method, I don't return a specific value, I just return. But that's going to be our base case there. If current node actually points at a live node, then what we're going to do is go and place our recursive call. So for this here, we're going to say this dot print newest first recursing, and for the argument we're going to pass, we're going to say current node dot get next node. So we're going to go through and have a recursive call to go and process the very next node on the chain. So we'll end up with a stack of all these recursive calls here going down to where we get to the very last node in the chain, and then when that one goes and calls current node, current is going to be null, so that's when we'll hit the base case and we'll start returning our things back up. After we have the recursive call, we want to go and print the contents of our current node. So this is how we're going to go through and get it so that the things that are newer on the chain, they're further down the chain, go and actually look like they're being printed first. Here I'm going to go and call system.out.println, and I'm going to go and say I want to print current node.getData. And we'll drop in some Java doc. So this prints items newer then current node, and then the current node. And current node is the node to start printing from. So this is the actual recursive method. For the one that goes and kickstarts things here, I'm going to make this one be a public method. Still going to be a void type though. And I'm going to call this one print newest first recursive as opposed to recursing. And this one's not going to take any parameters. And that is just so that it's easier to go and use it. All I have to do is just go and call this method here. I don't have to go and give it any arguments when I go and call it. It will take care of figuring out how to do the rest of the calls to get things started. So we're going to go and call our recursing method here, and that's going to be this dot print newest first recursing, and we're going to start off with this dot front node. In the case that we don't have anything in our queue, this dot front node will be null. So when we go and place that call, current node down here, the parameter will be null, so we'll just return without doing anything. We'll give some Java doc for this method. It goes and prints contents of queue with newest items first. Now, where our loop-based implementation had a pair of nested loops and ran in big O of n squared time, this one here is going to have just enough function calls for the number of nodes that we have. This one is going to run in big O of n time, not n squared. So this one's got better performance characteristics than our iterative approach with the loop. Let's also go and implement a recursive approach for printing our oldest nodes first. So this is going to be where we go through the chain in order. I'm going to do this as a public method to kickstart and then a protected internal recursing method. So I've got this protected method here we'll do first. I'm going to give this a void return type, and we'll call this one print oldest first recursing, and it's going to take a singly linked node of type T called current node for a parameter. The body of this method is going to look pretty similar to our newest first one, with one key difference. We're going to start off here by going and returning if the node is null, since that's our base case. So if current node is equal to null, we're going to go ahead and return. The difference between newest first and oldest first is the order in which we go and place our recursive call versus printing data. Here, we're going to go and print the contents of the current node first. I'm going to call system.out.println, and I'm going to pass current node.getData to be printed. Once I've printed out the value from the current node, then I'm going to go on to the next node. So we'll go and do our recursive call there. So we'll say this dot print oldest first recursing, and we're going to go and pass it current node dot get next node. And then we'll go and create our kickstart method here. So this will be a public void, and we're going to call this print oldest first recursive, and inside we'll go ahead and call our recursing method. So we'll do this dot print oldest first recursing, and we're going to pass it this dot front node. And we'll go ahead and give these some Java doc. So our newest first recursive implementation ran in big O time. The only difference between the oldest first and newest first is just the order of our print statement versus recursive call. Oldest first is also going to go and run in big O of n time. Now, granted, our iterative loop approach for oldest first also ran in big O of n time, but here we're not doing any worse, and we got the improved performance with our newest first recursive method. Sometimes what you will find when you go and implement things is that, a loop versus recursive, sometimes one approach just happens to work out a little bit faster than the other. Sometimes you'll see cases like this. Sometimes you'll also go through and see cases where you really want to go and have things be done iteratively with a loop, because you can end up getting swamped with the number of calls if you try to do things recursively. It really just depends on what particular case you're dealing with. There's not a one-size-fits-all answer for if recursive versus iterative is a better approach. Just so that you can see how these methods work, I'm going to go to the printable linked queue demo class, and here you can see that we're going and loading up the values 1 through 20 in our queue, and we'll just go and print them out. We'll use the recursive methods. We'll go and print our oldest first. And we'll go ahead and call this, or actually queue dot print oldest first recursive. And then we'll also go and print the newest first. So I'm just going to identify this as our newest first, and then we'll call queue.print newest first recursive. So when I go ahead and run this code, you can see we get the oldest first where we have the numbers in order, and then newest first where things are coming backwards because we're waiting to find out that our recursive call has run, which printed the version of the next item that's in our chain before we go and print ourselves. So that's why these two are reversed compared to one another. We just swap the order of those operations, and that flipped around our output. In the sample code for this lecture, I've written both recursive and loop-based solutions for what we just did with iterating over and printing the nodes in a queue, as well as recursive adding that we did earlier and calculating factorials. I've also included how to go and calculate the values for a Fibonacci series. So I would encourage you to go and take a look at this code, maybe try to run it, play around with it, see what's going on. For this lecture's participation project, I'd like you to create a program that can calculate the summation for an integer n, where n is greater than 0. Summation is where we go and add up all the values from 1 to n for all the integers in that range. You've probably seen this expressed mathematically before, something like this here, where we go through and have the big sigma, where we go through and add up from I equals 1 to n, and then I is our variable here. So every possible value of from 1 to n is what we're going to go through and add up. You can go through and kind of think of this recursively as summation for n is n plus the summation for n minus 1. And if we want to go and expand it out all the way here, you can see that we have n plus n minus 1 plus n minus 2 and so on until we get down to 2 and then 1. Thinking about this kind of more in a computer science standpoint, we basically have a formula that summation of n is equal to n plus the summation of n minus 1. And we know that by the definition of summation, the summation of 1 is 1. So I want you to go and create a recursive method that'll go and do the summation calculation. Your program should also have a main method. And in there, I want you to go and loop to print the summations for values of n from 1 to 100, including 1 and 100. Hopefully you have a little bit of a feel now for what recursion is and how you might be able to use it to solve some problems that you might go and encounter as you're coding. If you have any questions about this material, please join our Q&A session or send me an email. Thanks, and have a great day.